So, good morning, everybody. In this research presentation, I will discuss how it is possible to predict the structure of a frequency comb generated by a periodic signal that evolves into a non-linear optical fiber. And we will do that by using a simple neural network. So this work is the result of a collaboration between the University of Aston with Dr. Sonia Boscolo, with the University of Franche-Comté with Professor Jean Dudley, and myself from the University of Burgundy. So machine learning is everywhere in the media. We heard a lot about machine learning. It is widely implemented by the GAFAM, and it is possible to have tools to easily implement machine learning. And this machine learning is not restricted to the field of data science. It can be also very interesting in the field of photonics. Indeed, photonics can benefit from machine learning to imagine and design new components, and in the other way, machine learning can strongly benefit from photonics to improve its efficiency. So here we have potentially a win-win interaction, and we can have improvement in terms of devices or in terms of treatment of optical signals. And there are already examples that are implemented in the fields of telecommunication, of imaging, for the design of components or for ultra-fast optics. What we are interested in this presentation, this is frequency comb. So on one side, you can use frequency comb to do machine learning. There are examples where different wavelengths that are emitted by a device comb are used and are multiplexed to enhance the possibility of artificial intelligence. But in our case, we are interested more in the opposite problem. This is to use machine learning to predict and design frequency comb. So there are different ways to do so. You can have frequency comb from micro-resonators with plenty of spectral line, and there are recent examples where artificial intelligence has been used to tailor the meta dispersion of the micro-resonator and to enhance the flatness of the resulting comb. Another way to produce frequency comb is to involve electro-optic modulators. And here there have been also techniques that can use, for example, deep learning that have been successfully tested and implemented to obtain very flat combs. In our case, what we will use, this is the evolution of an initial signal in the propagation in the fiber optics. So our goal, this is to start from a simple excitation, typically a sinusoidal wave. And contrary to other techniques, to other example, we are interested both in the temporal and spectral intensity profile, and we want to have access also to the temporal and spectral phase. And we want both to predict the output of the propagation and to have an efficient way to find optimal solution for a given target. And as we are not expert in computing science, we want to use simple architecture. So to do so, let me first recall the physical effects that are experienced upon propagation in a fiber. So if you consider an ultra-short pulse, its evolution is governed by the nonlinear Schrödinger equations that takes into account the dispersions, the Kerr nonlinearity, and also in its extended version, some potential gain and losses. And you see, if you take into account the various property of your fiber, as well as the various property of your input pulses, it's already quite a lot of parameters. And the first things that you can do before trying to implement a solution, this is to reduce the number of the parameter you have to consider. And for this, there are some very interesting scaling rules. In this example, you can start with seven parameters and reduce the number of parameters to only 3. And this is what we have done in some previous work. We start from normalized parameter that summarize both the property of the input and the property of the fiber. We implement a neural network made of several hidden layers, and at the output, what we wanted to know, this is the details of the temporal and spectral intensity profiles. So we have used around 100 of, uh, of points to discretize this output. And it works. It works very well. We can really efficiently predict what we have after propagation of a single pulse in a fiber. Here we see that when we compare the prediction of our neural network in blue, they are very close from what you can obtain from the NLSC equations using standard algorithms such as the split step Fourier. And the agreement is good both in the temporal and spectral domain as well as the normal or anomalous dispersion regime. And as the neural network is very fast, we can map in 3 dimensions here where the interesting conditions are if you want to find a given output. So it works pretty well. And similar approach, sometimes relying on much more advanced techniques of deep learning, have been published in the last years. So what is of interest for us today, this is not to start from a single pulse. This is to start from a periodic initial condition that is typically here a central component that is surrounded by 2 lateral sidebands. And what is interesting as input parameters, this is a ratio between the intensity of this central component and the 2 sidebands. And the phase difference between the two are also of importance. And what we want to predict, this is the output spectrum. Here, just a few words on a specific case. This is when we limit the analysis to only 3 sidebands. So here, this is an ideal light for wave mixing, and it has been the subject of the work of some of our PhD students. So here, this is some advertisement around their work where they have been able to reconstruct the phase space of this interaction. So in the case of the work of Anastasia Shevaleva, it was by using experimental result neural networks. And in the work of Andrei Amoleliev, it was by involving data-driven models. In our case, in what we want to predict today, we do not restrict ourselves to only 3 components. We involved much more components, and we record both the real and imaginary parts of the complex spectral fields. And if we have this data, then we are able to reconstruct everything. So here we have not chosen to discretize both the temporal and spectral domain separately. We only focus on the COMP structure of the spectrum, and we record the complex properties. So this leads us to this kind of neural network. We start from four normalized parameters. Our neural network is made of three layers of around 30 neurons, and at the output, we have the real and imaginary part of each spectral line. The training of these neural networks went well. We have root mean square errors below 10 minus 3, and we have trained the neural networks with a very broad range of initial parameters. So we are able to cover a very large part of the space. And we can see here that the prediction of this neural network works very well. We have really a close agreement between the prediction of the neural network and what can be predicted directly by numerically solving the nonlinear Schrödinger equations. And the agreement is very good both in the temporal and spectral domain, in the anomalous regime of dispersion, as well as in the normal regime of dispersion. So now, if we want to reach a given COMP profile, how can we do to find the best target? So here, what we have used, this is really a very basic method, a brute force method, but it was just to show how a neural network can be powerful. So our approach, it was to start with 10 power 7 random input parameters. We calculate the output property using the neural network, and here what can be stressed is that the neural network is extremely fast. The output property we obtain them in only 40 seconds for 500 millionths of initial random values. And this is not using a large scale computer. No, this is only on a very standard personal computer using the CPU. From all this data, we evaluate the spectral and temporal property of our target, and we keep the best 10 guesses that we very slightly refine by the nonlinear Schrödinger equation. This is just to really minimize some errors, and this gives us the solutions. So here is one first example of the flat cone that can be physically generated during the propagation in the fiber. We say that the solution that we obtain is in close agreement with split-step Fourier method. And we can test also other kind of initial waves with, for example, carrier suppressed wave, and test both regime of dispersions. And what is also quite interesting with the neural network, this is as it is extremely fast, it enables us really to cover the full space, and we can visualize where the combination of interest can lie. So we do not only have the best solution, we have really a map of the solution that could be interesting to implement. So we can really have very quickly insight regarding, for example, the range of parameter that can be tested, we can directly see if the optimal conditions are on a very narrow range or if we have much more flexibility about it. And for this example, we see that the conditions to be implemented in the anomalous regime are very different from the condition that we should implement in the normal regime of dispersion, especially regarding the initial phase. Now, what else can we test? We can try to see if physically we can cancel the central components of our comb, and it is possible. We can also test if we can kill the two first lateralized sidebands, and we have found some initial properties that enables to suppress these two first lateralized sidebands. And we have the solution in less than 1 minute. We can also put conditions in terms of target in the temporal domain. This is what we have done here. In this case, we wanted to achieve the best compression of the pulse strain, so to reach the shortest pulse durations combined with the highest peak power. And we can see that using our neural network, we have reached very efficient compressions. And once again, we see that in the temporal domain, the prediction of the neural networks completely agrees with the prediction of the NLSC solved by the standard pre-step Fourier. And we see also that it works very well to reconstruct all the details of the longitudinal propagations. As a last example I would like to discuss today, in this final case, we have started with 3 lines of equal amplitude, so the same intensity for the 3 spectral line, and our target it was to maximize the energy in the central component. So it means that we wanted to have a spectral focusing, and we have found that it was possible to focus more than 80% of the energy back to the central component. So here we do not have a perfect spectral focusing, and we see that there is energy that is spread in the various additional spectral lines that appear. We can see in this example, once again, the agreement between the two approaches that is excellent over several decades. We can reconstruct the longitudinal evolution of this process of spectral focusing, and we clearly see that most of the energy is focused back to the central component. We can have the details of the temporal profiles, and when we plot the space of parameters that lead to the spectral focusing, what we see this is that we have to carefully choose the value of the initial phase. Typically, if we start from free in phase component, we will not observe the spectral focusing. Here we see that the phase offset that should be put in the lateral sideband should be close to pi over 2. So let me now conclude. What I'll try to show you this is that we can use a neural network to replace the usual modeling based on the nonlinear Schrödinger equation solved by the standard pre-step Fourier. And it enables us really a gain in terms of computation time. We can improve this computation time by at least 3 orders of magnitude. So with such a quick tool, we can very efficiently cover the full space of parameter and visualize where are the interesting solution. So it can be helpful really to better understand some processes. So I have shown, for example, spectral focusing, but it can be also the generation of extreme events. And we can imagine this kind of tools as a new way to produce interesting statistical approach. So if you want more details, please just have a look to this article that has been published in the special issue of Optics Communication, special issue that is devoted to the 50th anniversary of optical solitons in fiber. So thank you for having listened to this research talk.